concept into math. Looking at the same function again, let's imagine we want to find the area under the curve between these two x-coordinates. Let's further imagine that we will estimate the area using rectangles inside three equally sized regions. To translate this into math, we need labels for the x-coordinates that define the range of each of these regions. From left to right, let's call them x0, x1, x2, and x3. Now let's place a rectangle between x0 and x1 such that the upper right corner of the rectangle touches the curve at x1. The area of this rectangle is its height, which is the value of the function at x1, times its width, which is x1 minus x0. To estimate the area under the curve, we need to add to this the area of the rectangle in the next region, which is its height, the value of the function at x2, times its width, x2 minus x1. Finally, we need to add to this the area of the rectangle in the third region, which is the value of the function at x3, times x3 minus x2. Let's call this sum of rectangle areas capital S and give it a subscript of 3 to indicate the number of rectangles used in the sum. This can be written more compactly using summation notation with the variable j serving as the subscript and taking values from 1 to 3. The argument to the sum is the height of each rectangle, the value of the function at x sub j, times the width of each rectangle, x sub j for the x-coordinate of the right side of the jth rectangle, minus the x-coordinate of the left side of the same rectangle, which is x sub j minus 1. The width can be written even more compactly as delta x sub j, with the understanding that this stands for x sub j minus x sub j minus 1. Three rectangles do not provide a very good estimate of the area under the curve from x0 to x3, and so we might want to include more rectangles. To do this, take the height of the jth rectangle times its width and sum from j equals 1 to an arbitrary number of rectangles n. This is S sub n, a sum of the area of n rectangles, and is called a Riemann sum. The number of rectangles could be 6, 12, 24, or any other number. But S sub n only becomes a good estimate of the area under the curve if we take the limit of this quantity as the number of rectangles, the value of n, goes to infinity. In the limit of including very many rectangles, S sub n is the area between the curve and the x-axis from x0 to x sub n, and is written symbolically as the integral from x0 to xn of the function f of x times an infinitesimal width dx. This is the Riemann definition of an integral between two fixed limits, sometimes called a Riemann integral. In the integrand, f of x is the height of an infinitesimally narrow rectangle, and dx is the infinitesimal width of that rectangle. As we have learned, a Riemann integral can be interpreted geometrically as the area between the curve and the x-axis on an interval, but this is only true if the function lies above the x-axis. For instance, this function lies above the x-axis between x equals 0 and x equals 1.185. The Riemann integral over this interval is positive 1.121, and it can be interpreted as the area